Well, we're just about there. Welcome back, everyone. And it's official. Looks like we can start. Well, congratulations on being most of the way through the very first week. Some of us might have class tomorrow, but we're all mostly there. Usually week one is kind of overwhelming, but it's going to be pretty much the same kind of pattern how we've been doing the class last couple of days, all the rest of the way through. We are nearly done with section 7.1. I think it's just about 3 more examples we're going to take a look into. And then we're going to turn it over to what's really kind of a glorified review topic of U substitution, but we'll see how that works with specific integrals that just have one of the 6 or several of the 6 trigonometric functions inside the integrand. So really just more practice with integration today. Seems like that's what we do for the whole course when you're looking into the first couple of weeks, but we do get into quite a lot of applications. It's not going to be integration every single day. But any questions or comments at all before we get started? Okay, let's delve in. So here's the big punchline of integration by parts. If I'm going to try to write it down as compactly as possible, that's probably what I would write. There's side work of you have to take a differential of a function u. The other side work is you have a differential equation, but you integrate it or find the antiderivative to get the function v. We pick u by the LIATE mnemonic, which is usually pretty foolproof for the kind of problems that I would ask in homework and on the exam. And then down below is the entire formula. The integral of u dv is uv minus the integral of v du. So that's the whole idea. And well, let's get started, unless there's any last questions or comments. Okay, well, here's where we left off. There's a lot of practice problems on this, but there's a good amount of variation to the kind of problems you could see with integration by parts. So that's why we're doing so many of them. We'll do some definite integrals at the very end. We looked into how this mnemonic here helps us out on picking the right function for u. And the idea is it's kind of like order of operations where there are precedences here. In other words, L should pick our function u if it occurs somewhere in our integrand. If it doesn't, we just move down the line for I, inverse function. If it doesn't, move on down the line A for algebraic and so on. But this time, a logarithmic function does occur. It's right there, natural log t. So this one's going to be different than all the others we've done so far. We pick u equals natural log t to start out. After we do that, the next part of the table that we're going to complete is we need to have something for dv. It's the remaining part of the integrand, including the dt portion. So dv is t cubed plus 2t dt. Our parentheses here really matter because, once again, dt is like an ordinary algebraic structure and needs to be allowed to distribute through. So aside from the acronym, the other side of the way people like to think about this is a good way to pick u is when you go to find the differential, the derivative of that function should become something much more simpler. The natural logarithm is a pretty complicated function, but if you take the differential, du, you just get 1 over t dt. That tells us we're probably on the right track with this. That looks to me like it's reduced a decent amount in complexity. It's now a power function, t power -1. And different way to think about this is if you put natural log there for dv, you need the antiderivative of the natural logarithm. It's good to pause and think about that for the moment. What's the the antiderivative of natural log t dt? Well, to solve that, that's in the reading, if I recall correctly. That's integration by parts on its own, kind of like how we did cosine inverse. That one's t, natural log t minus t plus a constant. So that's not an easy thing to put right here. If you put natural log t here, coming up with its antiderivative, that feels like a whole drawn out process in and of itself. Probably wasn't a good choice to put it in that portion at all. But antiderivative of this, not so bad. We just use the power rule in reverse. Antiderivative of t cubed is a fourth, t power 4. Powers increase on the antiderivative. So that's power 1. We increase it to t power 2 and just write it as t squared. And then we're done. Visualize taking the differential of this just as a double check. Take a mental derivative. And we would get t cubed plus 2t. Will we differentiate that part there? So that's the side work. Once all the side work is done, we just use the formula. Integral of u dv equals uv minus integral of v du. So we are indicating that the whole u in this is natural log t. This is together t cubed and dt form dv. I guess that's kind of hard to put up here in the notes. So I'll leave it that way rather. Let's maybe write out this just to indicate. Here's the u, here's the dv. I think it's a better way to notate it. So u is natural log t. T cubed plus 2t is the entire dv portion. Then we expand it out further. The right-hand side of integration by parts formula says all this is equal to uv minus the integral of v du. So lots of parts, but that's guess why it's called integration by parts. There's a lot of moving parts here. We'll throw in the u du and the v portions following that color coding using these functions we have on the right. So here's the substitution. For u, we've got natural log t. For v, we've got a whole bunch more. Here's all that stuff. A fourth, t power 4 plus t squared. So this entire uv portion, what it boils down to is just going off diagonal here this way, multiplying. Multiply those two together, and then we go minus the integral of the v du portion. If you're the fan of the arrows way of looking at it, it's just taking this and multiplying that way. Substituting it in, that's just going to be 1 over t times 1 over 4, t power 4 plus t squared dt. So this is the 1 over t dt part. And that's the v portion. So all of it's substituted inside. And usually when you're doing this, I'm writing it out for the sake of a paper trail and notes. A lot of people would just simplify this, call it a fourth t cubed plus t when they go to write down this integrand. So if you do that kind of simplification, that's a good step saver. Well, last thing to do is simplify this, integrate, and we're on our way. Keep in mind, just because they're multiplied doesn't mean integration by parts, again, is a good idea. If you can simplify the integrand, you always want to do it. We didn't simplify here because that really is its simplified form. Distributing natural log inside that, it's not going to make the work easier. It just means integration by parts twice. So it expands on the work a whole lot. So that really was the simplified form. But that's not great for integration. We're going to rewrite this all as natural log t 1/4 t power 4 plus t squared minus antiderivative of 1/4 t cubed plus t dt. So now we can really work through this in a fast way. The last integral right here, that's just once again the power rule in reverse. So the end answer, the way I'd probably leave it would be in this form. Natural log t, 1/4 t power 4 plus t squared. I would probably just leave that in its factored form just like that. Then here, go term by term. Keep in mind we have to write this down correctly algebraically. Because there's two terms, there now has to be a parenthesis to allow negative sign to distribute through. If you forgot that parenthesis and it's like, say, an exam 1 problem out of 5 points, that's kind of low stakes. Maybe that's a half a point, but good to get it all in there without missing a sign error. So this portion right here, power is now 4. Divide by 4, and we're looking into a 16th, t power 4. And same song and dance. The power is 1 here, so now it's t squared divide by the exponent 2, so it's a half t squared, plus a constant, and now our work is complete. And you could distribute the negative through this. I don't think that's super important. Distributing natural log through, in my opinion, that just makes it more complicated. I think it's kind of nice in that factored form. I would just leave it right as it sits, right at that stage. Doing any distributions isn't going to really simplify it further. There's no terms to combine and so on. So this one would form a pretty decent problem as, let's say, an exam question. It didn't go too long. There wasn't multiple stages to it, a U substitution in the middle. But it was tricky because sometimes we just don't expect to pick U as a natural logarithm. So this is the odd one out in this lecture notes exercise set where we really needed to start that way to get going. Well, we did it, folks. That's the first problem of the day. 11 minutes in. These are kind of longer problems, but any questions or comments at all getting through it? Okay, well, I have one more where it's an indefinite integral. So I guess it was 4 problems left in these notes. And then 2 more definite integrals just to see what that new variety looks like when we're looking for areas under the curve. So here's our next one. As an indefinite, oh, I guess these are definite integrals. I just forgot. Here's our new landscape of definite integrals. Well, the reason we focus so much on the indefinite integrals is we're mainly just trying to focus on integration by parts itself as a technique. And now we're just adding on, well, what if you had to integrate your result? What would that look like? So there's a particular set of steps that go along with that. And really, there's 2 schools of thought. One school of thought is just do the antiderivative exactly as we did on the problems above. Whatever it is, drop the plus c because you're going to evaluate it from 0 to 2. The simplest form will do the job. The other school of thought, the way the author will do it, you'll notice in the reading is, once you get one piece done, you might as well evaluate it from 0 to 2. That saves a lot of writing. So we're going to go that route. But at the end of the day, it's the same kind of idea. We have x times the exponential, 5 to the power of x. X is an algebraic, so it's already at a in our mnemonic. E is the exponential, the one to the furthest right. The reason it's the furthest to the right is when you differentiate an exponential, at best, the complexity doesn't change if it's e to the power of x. And at worst, it just gets more complicated. If it's, say, 5 to the power of x, the derivative is 5 to the power of x times natural log 5. It just starts adding on constants when you differentiate. So that's why the exponential is the last choice, essentially, on this entire mnemonic. Here, we'll pick u is just x. That's the algebraic portion going inside right there. That informs us dv is everything else, 5 power of x dx. And this is a good one to review since I don't think we've had this come up yet. Everyone is pretty great with the derivative of e to the power of x because it's like the world's all-time best derivative. The derivative of that is itself. But this one's easy to kind of get foggy on because I feel like it just doesn't come up enough. Let's write it down as a formula. Derivative with respect to x of base b to the power of x is base b to the power of x times natural log b. So that'll help us on finding the antiderivative. That's the derivative formula. So now coming down here, once row 1 is decided, row 1 is just based off what you see in the integral. Row 2 is differential first. du is 1 times dx, which we usually simplify as just dx. 1 times dx doesn't hurt either if you wrote it that way. And over here, we take the antiderivative. We're going the other direction. The antiderivative of 5 to the power of x is itself. And because we're taking the antiderivative, we don't multiply by the natural log of 5, we divide by it. Or we can take 1 over natural log 5 just as well, and that would do the job as well. So if you came back here and checked with differentiation, you'd go through 1 over natural log 5, constant multiple rule. Derivative of 5 power of x would be 5 power of x times the natural log of 5. And that natural log 5 here cancels with that fraction here. So we would get back to our original differential equation above. We've got it, folks. That's our table for all the side work on this one. Any questions on putting these components together? Okay, next strategy. If you're just really good at this, you might just go x times 5 power of x divided by natural log 5, put it all together. When you're learning it, just so it can kind of get into your mind, it's not a bad strategy to go uv minus the integral of v du. So you can see how it all combines where things plug in. But there is more on this one, right? It's a definite integral. We're computing the area under the curve, x times 5 power of x. So whenever that happens, here's the only change we're going to make. This piece, u times v, it's ready to evaluate from 0 to 2. So we're just going to do the evaluation right here. And the second piece, integral of v du, it's still a definite integral from 0 to 2. So this is the only part that's new if the integral is a definite one. We are just evaluating a piece and one more definite integral right here. So like before, let's plug things in as we see them. uv, I'm going to write it in a slightly different form and take the constant out in front, 1 over natural log 5, then it's going to be x, 5 to the power of x, evaluated from 0 to 2. So the way I put that together was, I wanted the constant 1 over natural log 5 just factored out. You don't have to write this twice. All the action with the evaluation's right here. So this is kind of the simpler way to evaluate it. Save some writing, especially if that's a negative sign. It saves some issues with multiple negative signs combining. Then minus the integral from 0 to 2. Here's v, 1 over natural log 5, 5 power of x. Times du. Du is just dx. So it's all been put together. We just need to integrate one more time and then evaluate it like we're about to do here, and we're on our way. I think this is our first definite integral for the entire class so far that's actually come up where we're really evaluating it this time. Any questions at all, folks, to these steps so far? Okay, well, let's recall when we do these kinds of evaluations, we always go upper limit first minus the value at the lower limit. So this is the antiderivative. We're just leaving 1 over natural log 5 completely factored out side. Plug in 2, and we get 2 times 5 power 2 for 50 altogether. Plug in 0, and the whole thing is 0 because it's going to be 0 times 5 power 0. Then go minus. Over here, we need another antiderivative. If we can do it once, we can absolutely do it twice. If we needed the antiderivative of this, it would look the same, except we'd have to divide by natural log 5 again. So we would get over here 1 over natural log 5 squared times 5 power of x. Evaluate all of that from 0 to 2 once again. So that's the entire next antiderivative. And just like on the first piece we've already evaluated, I put parentheses around 5 power of x because I don't want to write 1 over natural log 5 squared twice. You don't have to. It's constant, leave it off to the side, and do all the evaluation right here at 5 power of x. Saves a lot of writing. It makes it much easier to simplify down the line. So on our next step, here we're just simplifying what we have. This is just a glorified 50 divided by natural log 5 minus, here a little bit more going on. Let me copy that constant out. 1 over natural log 5 squared times, this is 5 power to the power 2 minus 5 to the power 0, which is not 0. Let me control Z that. So this is a 25 minus 1 altogether. So just a glorified 24 where the red dot is. So the answer ends at 50 natural log 5 minus natural log 5 squared dividing into 24. So we've got it, folks. The claim is the exact area under this curve right here is that quantity. And we did it. Again, I think that's our first definite integral for the full semester so far. We're not that far in, but we'll be doing many more as we go. Any last questions or thoughts on getting through this one? Okay, well, because it's our first definite integral, it doesn't hurt to kind of connect some thoughts with this one. I don't know the numerical value of this number. It's kind of a complicated looking constant. So let's throw it into the calculator just to see how reasonable is our answer. 50 over natural log 5 minus 24 over natural log 5 squared. That's what I wanted to see. I was hoping to get a positive number. The reason for that is our integrand is a non-negative function on the domain from 0 to 2. So finding the area under that curve, x, 5 power of x, it better give us a positive number, right? So if that was negative, something's gone horribly awry. And now just to emphasize, let's throw in another curve, y equals x, 5 power x. That's not what we want. We have to center this around the limits of integration. So change the domain from 0 to 2. And it's exponential. I should have thought about that. It kind of shoots up like this, and the area under this curve, it's kind of hard to visualize, from 0 to 2 is exactly that there. That's the approximate down below. So if you're doing a problem like this on the homework setting, it's pretty fast to get a good visual. Throw the constant in to see if it's appropriate. When I'm grading these on homeworks or exams, I'm really going for this right here. This gets you full credit, but it's not a bad idea to be curious, see what that numerical value is to see if you're on the right track. Well, we have one more to go. Then we're going to switch gears from integration by parts to something else. But any final comments on getting through this one? Okay, so here's the actual last one for the notes. I forgot how many problems there were left over. Part B is kind of a challenge question. And it comes out with a decent hint as well. Occasionally, when you're looking at the homework assignments in this class, I try to give hints as well for various exercises. I think I gave a hint on the section 7.2 for one of the exercises. And in these kind of contexts, the hints are usually extremely strong suggestions, more than just a hint. It's more of a, hey, you really should try this. Try a U substitution before you do anything else on this one, and hopefully things work out. But that's a weird comment still, right? Do U substitution on this. It doesn't seem to fit the U substitution landscape whatsoever. There's a function side of another function, but if you take the differential of that function, there's nothing else in that integrand to work with. So kind of the punchline with this kind of problem is that U substitution as a method is wildly versatile. And that's what this problem is attempting to illustrate. If you're taking other math classes like, say, mathematical statistics, probability theory, probabilities are just areas under curves. And this kind of thing we're about to do, it actually comes up a lot. So this one's a bit of an adventure, a very bad exam question, but a good skill builder for us to go through as a class. So doing it as a U substitution, the most logical thing to try is still try to pick out an inner function. Square root of x does the job. So if u is square root of x, the immediate thing we do next is calculate its differential. Du is the derivative of square root of x. And we mentioned this one time, but let's say it again. If you take the derivative with respect to x of root x, it's the derivative of x power 1/2 really, which becomes 1/2 x power negative 1/2, which becomes 1 over 2 x power positive 1/2, tracking through exponent laws, power rule in reverse, that becomes 1 over 2 root x. But this derivative comes up enough times that this to this is a worthy shortcut just to have at the ready. So we don't have to reverse engineer it every single time. So this is a shortcut. This is the second time where I've used it. It's a shortcut I use quite a bit for that derivative here. So now the differential becomes 1 over 2 root x dx, which means it feels like we're not on the right track at all, right? When we look at this, actually want to change the color coding just a little bit here. So this looks bad because there's no 2 root x over here, but then this is, we call it a differential. It's also an equation, and you can do whatever you are allowed to do with ordinary algebra in this equation. One thing you can do is, let's just isolate dx. Then you're allowed to use this whole thing. So multiply both sides by 2 root x. 2 root x du then equals dx. So that looks good, but if we're changing dx into du, anything that involves x is no good to us in u substitution. Here's where the weird step comes into play. U is root x. So you actually can write everything in terms of u in this particular situation. Substitute right here inside the differential that we've rearranged. We get 2u du equals dx. Again, to me, that's kind of weird. It's interesting that you can actually do that. The algebra just works out perfectly so that when we swap out dx, everything in this integrand will really involve nothing but u. So that means we're on our way with this one. Any questions before we go to the next step? Okay, next thing I would do is sometimes undoing the substitution is not a great idea when it's a definite integral. Our author often doesn't, so I like to do these in a way that makes the reading more compatible with what we're actually going to do in class as well. And the reason the author doesn't undo the u substitution is it's always better to change the limits of integration. In section 7.3, there's several problems which will be extremely painful if we didn't do that. That unwinding multiple substitutions is a very laborious process. So a really good idea, good principle is, if we're doing a u substitution on a definite integral, also change the limits of integration. X is going from 9 to 0. The answer is just an area, so we can leave it in terms of u. We just need limits of integration for the variable u. So if x is 9, go back to where u is. That means u is the square root of 9, which is 3. And if x is 0, that means u is square root of 0, which is 0. And those will be our new limits of integration. So that's a good amount of side work already just to get started on this one. Let's come back here and say integral from 0 to 9 cosine root x dx now becomes the integral from 0 to 3 with the new limits of integration. Cosine root x is going to be, I'm going to write it just a little bit to the right and call it cosine u, root x turning into u. And for the dx part, go back to our equation for dx. It involves 2u du. 2 as a constant can go way outside the integral. There it is. U, I just wanted to go in front of cosine. I guess that wasn't important. You couldn't put it to the right of cosine. And then here's the du portion. So we've got u cosine u du. Double that integral from 0 to 3, and our work is done. That's weird, right? Because what we've done, what we've achieved is we took an integrand that looked kind of simpler because it's just a function composition, and we rewrote it as no function composition But now there's a product of functions, which we can't simplify. But in a way, that's okay because that's exactly what integration by parts is all about. So this one cannot be attacked by integration by parts. U substitution just sets us up so that we can finally solve it. So at this stage, integrate by parts. So this is like part one of the problem. We now have a nice integral that we can solve as an ordinary integration by parts kind of a problem. And the variables here are kind of inconvenient, right? This is u, and we usually go u dv when we set this up. But the variable names are superfluous. We can change to whatever name we want. So instead of starting off with a u in integration by parts, I'll start off with a w. So I'll have a w, a dv, then we'll compute the differential dw, we'll integrate both sides over here, and get the v. So once we solve that side work here to the right, this table, our work is going to be mostly done over here. We just need to pick a good w. Anyone see a good choice for w here to get this one started? Yeah, good call. We could try picking cosine, but the derivative of cosine is negative sine. It's equally complicated, maybe more with a constant. But good call. If you see something algebraic like x, x squared, or u in this case, that's an absolutely good one to reach for, unless there's a natural log somewhere in your integrand. So let w just be u. Differential of this would be dw equals 1 times du. I'll write in the 1 this time just to really emphasize u changed to 1 because the variable names are different. It just sort of feels different sometimes. So if that's our u, excuse me, if that's our w, then everything else is going to be dv on this one. So we're going to pick cosine u, du. Here we integrate. We answer the question of the derivative of what is cosine. That one's not so bad. Derivative of sine becomes cosine. There's no negative sign trickery with this one. We'll just go sine u. And notice we're going to stay in the variable u. We're just using new limits of integration. So we're never going back to u equals root x on this one because the integral is definite. So our side work is done, the integration by parts table. Next good call here is to write down the formula. But that 2 is kind of a pesky thing. It has to distribute into the entire result. So a big set of brackets, let's maybe go with parentheses. I think that'll visually look better, is a good choice, just so we make sure we distribute everything through. So take 2 times uv. Excuse me, it's not uv. It's going to be w and v. I forgot we changed the name on this one. wv minus the integral of, if we go this way, v dw. That's the formula, but recall it's also a definite integral. So we're going to evaluate this piece from 0 to 3 and also integrate from 0 to 3. So that's the whole formula, and we're going to multiply it by 2 at the very end. That's a lot of stuff altogether, but hey, we're integrating something that's really quite complicated. Cosine squared of x, that would be a really hard one to reverse engineer without going this method. I don't know how I would do it without that first u substitution. But now down here, it's all just a matter of plug and play. We have 4 components. We're going to plug them in exactly this order and get a result out. So following the order, I don't have colors for color coding, but there's a pattern every time, right? You go w times v. That's just going to be u times sine u. Evaluate that from 0 to 3. So if you write your tables down in the same exact way each time, even if your table looks different, your pattern is always going to look the same every single time. And it's less to kind of worry about each time you go through it. less cognitive load if you're always doing it in the same kind of pattern. Then minus the integral from 0 to 3 of v dw, that's going here times here. That just means it's sine u du. Close the parenthesis, and we're just about there. That's a nice integral from section, say, 5.3. We can solve that one. This one's a fast evaluation. Some of the numbers are weird, like sine 3, but we'll just leave it in its exact form as sine 3 and be on our way. So first, evaluate at the upper limit, 3. We'll get 3 sine 3 minus, put 0 here. Sine 0 is 0, u at 0 is 0, so it's just a minus 0 altogether. And then don't close the parenthesis because the 2 distributes through this piece as well. So we have sine u and a negative sign. Anyone see what should go here? Is it going to be cosine or negative cosine? Actually, I think this one is going to come out positive cosine, only because of that negative already together there. But yeah, it depends on how you're visualizing it. I didn't really ask the question right. You get negative cosine here, then it cancels with that negative, so the end result is positive. So yeah, absolutely negative cosine. So altogether, getting the negative cosine on this one, multiplied by the negative, we've got positive cosine u altogether. Then we take that whole thing, evaluate from 0 to 3. Close the parenthesis, and one last evaluation to get through. So we're almost all in our way with this one. We're taking twice the result of 3 sine 3. My 0 cancels off. This is going to be plus cosine 3. It's kind of a strange constant. Minus cosine 0. And the way I wrote that's not really convenient, right? This is mainly for the notes. We have to evaluate all of our trig functions for full credit on exam and homework situations. So cosine 0 is 1, and that's the last thing I have to write in. 2 times 3 sine 3. If you put a 1 in right there by the red dots, then good on you. That's a good time saver. Plus cosine 3 minus 1. And just to reiterate that for the sake of the notes, as a reminder, we must evaluate all trig functions that can be computed exactly on homework and exams. So if it was cosine 3, that's a good one to just leave in that form. That's the most exact way we can write it. If you have cosine pi over 2, cosine 0, cosine pi over 4, any of those values that we know from trig, we can compute exactly. Those are the ones we're referring to. And like I mentioned before, if this is an exam problem and you've left it as cosine 0, you might lose a half a point. Just as a reminder, we do have to do those evaluations. It's not going to be something that's going to really chop you down on an exam. Well, we did it, folks. That's our last one. This one is really 2 problems. It's the problem of set up the u substitution, and problem number 2 is do the integration by parts on a u cosine u. But the bigger takeaway, once again, is u substitution is an extremely versatile technique. And that's part of the reason why we're just revisiting that as the core technique of section 7.2. All it really is u substitution. But any last questions, comments, or concerns whatsoever before we switch over to that next section? Okay, well, congratulations as well, folks. We did it. That's our very first section down. Many more to go. This one was longer for us because it was part review, part really starting section 7.1. The next section has a good amount of problems too, but we're not going to take as many days getting through this one. This one, it won't be too bad. Like I mentioned, it doesn't have a new technique, but there's new information to work through. When you're doing this section, if your trigonometry feels a little bit rusty, for me, it's been a year since I taught trigonometry, so I already feel the urge to review some of this stuff. It's always a good idea to refresh on your trigonometry. In your own calculus textbook, it has a very nice appendix on trigonometry, which gives you a nice run through. If there's any spot that you feel like is a little bit weaker, simplifying identities, trigonometric identities like addition formulas and so on, that'd be good to recheck. And I made an attempt here of putting down the main things that I would say be aware of for the purpose of Calculus 2, Calculus 3 on these notes here that you can visit. So we'll cite the review information as we go, because once again, for trigonometry, it might have been a while. It's one of those things that you just have to keep on refreshing as you go in these kind of classes. So I put here, just as a refresher as well, here's the derivative of the 6 ordinary trigonometric functions. We have the nice stuff like derivative cosecant is negative cosecant x, cotangent x. You prove that by using either chain rule or quotient rule. And same for pretty much all of the 4 down here. These 2 are the hard ones that I think section 3.3 takes a lot of time to prove. But now when you turn all this around, if you're finding the antiderivatives of the 6 trigonometric functions, some of this gets a little bit weird the closer you look at it. Say, for example, we know antiderivative of sine is negative cosine. We just use that result, for example. Very last problem. Antiderivative of cosine is sine. This one might be surprising. Antiderivative of tangents, natural log secant x plus a constant. But that's u substitution. You just write tangent as sine x divided by cosine x. Let u be cosine x. Go through the entire u substitution. And that's what you get out. This one feels different, right? It's a sine x. But that's properties of logarithms working for us, because you could rewrite this one as cotangent x. Dx is negative natural log cosecant x plus a constant. But that includes an extra negative sign, right? That's kind of irritating. It can simplify. Negative sign becomes an exponent. Not cosecant inverse, but cosecant to the power -1 is sine x. So that's why they look kind of different. They're just off by a negative sign is all that's really going on there. Now, these are the ones to me that seem really bizarre. These are strange formulas. Antiderivative of secant. Well, the derivative is just secant x tangent x. But notice how many natural logarithms we have in this whole process. And this one is natural log secant x plus tangent x plus a constant. Those are really weird. And I feel like it's weird enough. We should do that one. If you can see how that one goes, you'll have a good idea how the cosecant one goes as well. Well, any questions first about the table before we investigate the secant x version? Okay, well, pretty much everything from tangent to cosecant, secant, cotangent, it's all u substitution. This one is a u substitution, but it's one of the weirdest u substitutions we've seen so far. We have to start with something nice like secant x, make it look way worse, and then u substitution is finally on the table. So here's what it looks like. To derive this antiderivative, we take what we started with, secant x in the integrand, and we multiply it by the weirdest thing ever. This is one of those things where I've just seen this done once. I would never come up with this on my own. If I was lost on a desert island and this is how I had to get off to solve this, this could take me decades. I don't know who came up with it originally, but if you take secant x plus tangent x, divide by secant x plus tangent x, that does the job. And again, that's very bizarre. We're just running through this for the sake of the derivation. but also to show how U substitution works in these kind of problems. So now that it's in that form, I multiplied by 1 essentially. We can multiply across the numerator and get secant squared x plus secant x times tangent x divide by secant x plus tangent x. So that's our new integrand. It looks completely just inappropriate to make something that complicated, but for the sake of integration, that's its simplest format in U substitution. Now, when you look at that, it pays to look at this table above. Notice that secant x tangent x is right there. You could take the antiderivative of that thing and get secant x if you're only focusing on that one piece. You can't ordinarily just take antiderivatives piece by piece like that. But likewise, a secant squared comes up. Antiderivative of secant is tangent. So that's kind of nice in a way. If you look at that denominator, derivative of that secant right there is secant x tangent x. If you combine it with tangent, the derivative of tangent is that secant squared right there. So somehow, some way, that's the most convenient denominator in the world to have in the landscape of U substitution. So let's write out these steps. If U is secant x plus tangent x, then du would become derivative of secant is secant times tangent. So this becomes secant x times tangent x. Derivative of tangent is secant squared plus secant squared x, and then dx. And miraculously, that's exactly what we've got in that integrand, right in the numerator. So that entire portion here to here is just 1 du altogether. So the differential is done. We just go back and use substitution, pull everything together. The result is integral of 1 over u du. Following the color coding, that's where secant x tangent x went to just u. And everything along the top here, that's just du. I usually color coded that a little bit different. Let me do the same as we did before. Du to keep that blue there. So once we're there, now we have a nice antiderivative. The derivative of a natural log of x, say, is 1 over x. So the antiderivative of 1 over u is the natural log of the absolute value of u at a constant. Then we just plug in what we said u should be, secant x plus tangent x. And this becomes natural log of secant x plus tangent x plus a constant. So that's our full-on antiderivative. So it's kind of a nasty one. The derivation is bizarre, multiplying by that piece. But once you get started here, pick the U substitution, this portion here is the kinds of stuff that we're going to be doing in this homework, the lecture notes, and a typical exam problem, moving forward from there on down. And just to double check, that's exactly what we picked up. If it's a cofunction, we just put a negative sign in the middle and change from secant to cosecant, tangent to its cofunction, cotangent. So pretty bizarre. I would say that this table is a great table for, let's just say it this way, great for exam notes. Because this is a table, especially these entries here to here, that you don't necessarily want to reverse engineer any of them from scratch. You're always welcome to just go right to the punchline. You never have to show work for antiderivative tangent. You never have to show work for antiderivative secant or cosecant. In other words, we'll take all of these for granted. But now this is a great place for section 7.2. We never had the full table of antiderivatives in Calculus 1, not even close, but now we've got them all. So what we're going to do is just go forward and see what other kind of antiderivatives we're going to take. first order of business was to fill out this table. And for the section title, trigonometric integrals, we're going to be meaning integrals that look like this. Sine squared cosine x, or maybe sine power 5 cosine power 6 with the input negative 3t, and so on. Different kind of combinations of sine and cosine functions. We'll do the same for different kind of combinations of secant tangent functions, and that will be kind of the roundup for these notes. This one will be just for extra practice. Well, the reading has some pretty challenging problems, some interesting derivations, and here's where we're going to start. Strategy for evaluating powers sine power mx times cosine power nx. There's some great strategies for finding these antiderivatives whenever they come up, but it's a three-part strategy, which is kind of concerning in a certain sense. So let's go through these carefully to show how the strategy works. At its heart, they're all U substitutions. I guess I picked a different color there. Green for our U substitutions in these notes. So let's look at this strategy pretty carefully. But also one thing I want to mention is, if you don't like this strategy too much, that's really okay. A lot of times you can pick a U substitution just by figuring out what's going to stick, what's not going to stick. All this is giving us is a definite method in certain cases of what to do, depending on what's going on with the exponent on sine, what's going on with the exponent on cosine, the m and the n in the problem. I feel like I highlight these kind of weird. So here's the strategy. If the power of cosine is odd, I think that should be in yellow as well. Odd just means 2k plus 1. We're actually going to come back to that in chapter 1, but that's just the generic form of an odd number. Add 1 to something that's been doubled, therefore even, and that's your formula for odd. So if you spot an odd power of cosine, even just cosine, that's power 1 for odd, that's going to be a U substitution which will work, sine x. If the power of sine is the one that's odd, then cosine, the opposite function, should be what we should use for U. And if they're both odd, sine and cosine, then either substitution will work. You have multiple formats for your answer. You're just at that point trying to pick the way that's going to give you the least amount of work that you have to do algebraically and with the integrating. So odds are what we hope. That's our hope of hopes in our integrand. If a cosine has an odd power or a sine has an odd power, there's a definite road for U substitution. But U substitution can also actually fail just completely, and that's when both powers of sine and cosine are even. We don't use U substitution, we use these formulas. Sometimes in a trigonometry class, these are referred to as the reduction formulas. So if you've heard them that way, let's label it. Reduction formulas. What they're reducing through that namesake is the power on the function you get. Sine squared is a half times 1 minus cosine 2x. You prove that with the addition formula and just doing a bunch of algebra to solve for sine. And likewise, cosine squared is a half 1 plus cosine 2x. And between these two formulas, we'll use them quite a bit in this section, homework. They can come up on exams. Notice that the only difference is a negative here, a positive here. So if you've memorized one, you have the other by just changing the sign over. Sign is associated with the negative. Our author also calls out this formula right here. This one is a half angle formula. So out of the gate, we're using a lot of trigonometry in this section. So that's why we're taking a good amount of days on it. You notice in the notes, because there's a good amount of trigonometry just to review. This one's called the half angle formula because we went from 2x to just x. The angle is x, it got halved from 2x to x. So that's one reason to call it that namesake. Again, if you ever had to prove that one, you just write down an addition formula, and that's the whole proof on that one there. So the addition formulas for trigonometry give you just a whole smattering of other stuff. So if we have even for both sine and cosine, that's when we're using other trigonometric identities to maneuver through the integral. And we'll show a case as where that comes up on these notes as well. Well, that's the discussion of the strategy. So first, you want to look for odd powers. On this problem, cosine is to power 1, which is odd. It tells us substitute the other function. So that's the whole strategy. And this one, we would say cosine is odd. Therefore, you should be sine x. And we're on our way. That's the u substitution, which is guaranteed to work. And like I mentioned earlier, if you don't care for that strategy, trial and error works just as well. Sometimes you can stare at this for a few moments and determine, yeah, sine x is the only one that's going to work. Because when you take the differential, du, you get cosine x dx. And cosine x dx is right there in your integrand. So that's the only one that's going to work. Change this up. If you say u is cosine x, that one's just going to fail immediately. And you'll see right the reason why when you calculate its differential. So that's half the story so far. And you know what? I guess we're kind of ready to go on this one. Any questions or comments at all, folks, with the u substitution? Okay, other side to this story is we don't have to undo the u substitution. This one's a definite integral. If you decide you do want to undo the u substitution, then you're evaluating from 0 to pi over 3, and that works just fine as well. So if that's your go-to method, you don't have to change it. I'm just trying to write out the work that's very similar to how you'll see it in the reading. And I also personally agree that in certain cases, this is the faster way to achieve the result. Either way, your work is going to be 100% equivalent. So the steps I would make next is write x equals pi over 3, x equals 0, those are our limits of integration. We're going to change them to limits on u. So u is going to be sine pi over 3. Like we mentioned in the last section notes, we do have to compute these valuations. Sine at pi over 3 is square root 3 over 2. So that's one that we can compute exactly. Then down below, if x is 0, we just substitute back here, 0 for x. It's now sine 0. Sine 0 is 0, so those are our brand new limits of integration. Then come back over here, we're kind of on our way with this one. So we're going to go from 0 to square root 3 divided by 2. And I had this highlighted. Let me go back to how it was. In place of where we see sine, that's just going to turn into a u squared. So the power 2 here is really saying sine x all together squared. So u squared would be sine squared. Then cosine x dx, that's just the du in the problem. And the whole integral has just now boiled down to integrate u squared. Kind of the nicest all-time definite integral ever, right? This is now a problem that you would see in section 5.3. And that's what our u substitution has done for us. It's reduced the problem. So to solve this one entirely, we just need an antiderivative here. We can go 1/3 times u cubed. I'll do that times a little different. Let me throw a parenthesis on it. We're going to evaluate u cubed from 0 to pi over 3. So now this is, excuse me, I must have been looking at the wrong one. The actual limits of integration, we changed them, right? It should be root 3 over 2. Let me fix that there. Root 3 over 2. So 1/3, you can leave factored out in this format, and it becomes 1/3 of root 3 over 2 cubed minus 0. So that's u cubed evaluated from the upper limit to the lower limit, where we just got a 0 altogether. And we're pretty much done. We do want to clean this up. We shouldn't leave an answer that just says minus 0. That's an immediate simplification, right? And that one simplifies. It's absolutely 8 in the denominator. And then it's square root of 3 cubed. There's a lot of roads to simplify that. If you just left it as square root of 3 to power 3, I'm completely fine with that. Some people might write this as root 3 cubed as 3 to power 1/2 cubed as 3 to power 3/2. So if you go that route with exponent laws, totally fine. I'm not super picky about this. One really clean way to simplify this, if you want to just practice exponent laws a little bit more, is you could write cube root of 3 cubed as this, excuse me, I said that weird, square root of 3 cubed as square root of 3 cubed in this kind of way. The power 3 commutes on the inside. You can actually swap these around if you want to. They commute, which is kind of nice. Then you'd be dealing with the square root of 3 times 9. You can take the root of 9, becoming a 3, root 3. But again, that's if you're just trying to match the answer exactly to what you would see in the back of the book. If you left it like this, or even like this, you've got the right area either way. So we were just taking this as an opportunity to just brush up on exponent work. This becomes 1/3 times this thing, cube root of square root of 3 cubed is 3 root 3. Then 2 cubed is over 8 altogether. That gives us a nice cancellation. And we get exactly root 3 over 8. And if you did this in a slightly different simplification, you might think you have the totally wrong answer. But throw it into the calculator, compare numerical values. It doesn't mean you're wrong just because you formatted your exponents in a different kind of way. But either way, we've done it, folks. Now we know if this ever comes up in your life, the area under the curve, sine squared x, cosine x, from 0 to pi over 3 is root 3 over 8. And even though that sounds kind of silly, we know from experience areas can be anything. They can be densities, they could be energy, they could be force, they can be distances, anything whatsoever. Take another look at the net change theorem in section 5.4. Areas can be any physical quantity whatsoever. This just didn't have any context to go along with it. So that's how to get through this one. Any last questions or thoughts at all, folks, surviving this problem here? Okay, well, here's our next one to give a try on. Not all of them are as straightforward as we would like. This one's a little bit tougher. But let's mention what our big overall arcing strategy is. If you spot an odd, here it is on sine, pick the other function. Our u should be a cosine function. So u should be, on this one, cosine of -3t. Not to power 6. Make that always to power 1. This will just convert to u power 6. And this is kind of a longer problem to solve in its entirety, but I want to give you some hints on how we're going to have to rearrange these things and really solve them. So instead of trying to race through this is a good problem to do carefully. Here's the next strategies you ought to take. And good problem to challenge yourself with if you're having trouble sleeping, if you're bored or anything like that. Try this one over the weekend. It's a decent challenge, I'd say. Once you pick your u, the rest of the problem is mainly organization, really. If u is cosine -3t, then du is going to be, well, it's a differential that involves sine, right? Sine is part of the problem, which means you need to give away one factor of sine here to go along with the differential you're going to get over here. There's just no other way about it. So we reorganize our integral and write this as sine to the power 4, -3t, cosine power 6, -3t, times sine -3t dt. Although you don't have to take this middle step that we wrote in here, it's probably a really good idea. There's so much organization that goes along with this. So if we take our differential right here, derivative of cosine is a negative sine of negative 3t. It's not the whole story because it's also a chain rule. Chain on the derivative of negative 3t, which is negative 3, dt. And that's why we have to give away a factor of sine. One comes out right here when we take the differential. We can rewrite that differential as 1/3 du is sine negative 3t dt. So that's where that's all going. That's going to turn into the du portion right there. Let me write that as cosine power 6 with the 6 more clear to read. This whole thing, that's just going to turn into u power 6. But now we have one problem here, right? There's still an even value of sine left over. So the thing that we'll have to do next is we need more trigonometric identities on this one. We need the identities cosine squared x plus sine squared x equals 1. In other problems, we might need this identity, that tangent squared x plus sine squared x equals 1. And still other problems, we might need this identity, cotangent squared x, or hang on, I'm not sure what happened to this identity. Let me fix this one real quick here. Sorry if you're working in pen today. Tangent squared x plus 1 equals secant squared x. Sorry about that. If you're screaming at your monitor or internally, then that's the correction right there. And likewise, cotangent squared x plus 1 is cosecant squared x. Okay, so that's the full set of Pythagorean identities. We need the top row right here to get through this problem. So this is what the setup looks like. We'll review this when we come back on class on Monday and then carefully go through how to rearrange the identity, how to progress through this integral. But these are what the major steps look like. It's a lot of setup, but at least we know what we're picking u to be to start it out. Any questions or thoughts at all, folks, with what the setup looks like on this one? Okay, well, we'll end class a couple minutes and a bit early today. The other takeaway is, again, there's lots of trigonometric identities that show up, and these are the major fundamental ones. If you were like me and you forgot how to write down one, not a bad idea to include this on your notes for exams as well, just for extra reinsurance, because this kind of stuff comes up quite a lot. But have a great weekend, folks. If you have any questions while you're working homework, I'm available to interact over email, say on Friday. If you're working late on Friday, you have a question, don't hesitate to email at any point. I'll always check my email Saturday morning, Sunday morning, and that's just my habit throughout the work week and the weekend to just get through emails so I'm not bogged down on Monday. So don't hesitate to write. I'll be happy to help out. But otherwise, we're going to return to this section first thing on our Monday class. Have a great weekend, folks. We'll see you all later. Thanks. Have a good one. Yep, take care.
See you next week.
Yep, have a good one.